Hi everyone, this is ESR 10 of the PAM² project, Amal Charles. I'm based at the Karlsruhe Institute of Technology at the Institute for Automation and Applied Informatics, and the project topic that I worked on was the process optimization of the SLM process and other post-processing steps. So the next 5 minutes I will try to take you through what we managed to achieve within this topic over the last 3 years. So we start with the agenda. Firstly, one of the features that we decided to focus on from the start was the critical down-facing surfaces. So I'll begin by giving a short introduction to the topic, state of the art, the methodologies that I followed in conducting research on down-facing surfaces, the progress that we have made, and I'll also talk about some of the published results that we have worked on and the plans for future work. So the reason that we chose to work on down-facing surfaces is because they are notorious for having the worst surface finish among all additively manufactured surfaces, especially in angles less than 45 degrees. As you see in this picture on the right, the surface progressively becomes more unstable and rough, and therefore these low angles require printing with support structures, which necessitate further support removal processes. So the aim became for us to develop further process understanding to be able to print good quality low angle parts without the need for supports. As you probably know, the main reason for defects and a lack of stability in down-facing surfaces is due to dross formation, and dross is formed due to overheating of loose powder due to its low thermal conductivity, which then leads to excess melting taking place. We focused on using a down-facing printing strategy by varying process parameters within a specific zone adjacent to the immediate down-facing area in order to develop process parameters for low angles of 45, 35, and 25 degrees. Methodology that we followed include a DOE for printing a large number of samples, which were then analyzed using multiple microscopy methods in order to determine dimensional accuracy of the parts as well as surface parameters like surface roughness. We then used a generated data set for each angle scan strategy and used statistical methods to understand the influence of different process parameters, main effects, interaction effects, and we developed predictive equations that can be used to predict various quality. And then we also, to understand further the qualitative nature of dross formation, we also did SEM imaging to understand really the surface and melt pool physics in down-facing areas for various volumetric energy densities. Starting with the statistical analysis, we were able to plot interaction effect plots, which gave us an understanding of the various effect of process parameters on quality marks like dimensional accuracy and surface roughness. ANOVA analysis also helped us understand the most significant process parameter, and using this, we are also able to develop predictive slice plots, which were then able to can be used to actually predict different quality marks. The predictive slice plots we saw were made possible because of our developed quadratic equations here. So this is an example of what a quadratic equation looked like for us based on our regression modeling. And where here, for example, y denotes the respective output, and here x1, x2 all show the various process parameters. We then also conducted further validation experiments, which helped us test the accuracy of the predictions, and we received fairly good predictions, as you see here on this table. Moreover, we also created an ANN model using our data to explore its accuracy for our purposes, as ANN models have been in the past quite successful in modeling other manufacturing processes. This work was presented at the Special Interest Group meeting at the USPEN in 2019, where our model at that time was able to predict dimensional accuracy with only an error of 0.28 millimeters. Finally, currently we are developing our understanding on qualitative aspects of dross formation using SEM micrographs in order to explain recognizable features of low volumetric energy density and high volumetric energy density surfaces, so we can explain why roughness is high in low VED surfaces and why roughness is low in high VED surfaces. This way we can also give suggestions on optimal process windows based on VED for down-facing surfaces. We believe that we have pushed the understanding of the SLM processes, especially in down-facing surfaces, especially through the development of predictive equations and the further qualitative explanation of the mechanism of dross formation. Some work is still left for the future, especially to understand the positional orientation effects on quality in down-facing surfaces and the development of a unified model. Of course, there's also work that will continue to happen in the background with other ESRs even after the end of PAM². Finally, I know this presentation has not had a lot of details, so all the details can be found here through the numerous publications that were made possible by PAM² and easily readable through my ResearchGate or at the depository of KIT or at any of the open access websites. Finally, I'd like to thank all of my fellow ESR friends, supervisors, and of course, for making PAM² a thoroughly memorable, enjoyable, enriching, and successful project. See you around, and bye for now.